today we have basically we've gone over sections 4.1. Remember, we skipped 4.2. We had 4.3 and 4.4. So today we're going to start section 4.5. Just remember the big picture is that the whole chapter is about solving quadratic equations and different ways to solve quadratic equations. So that's what we're going to talk about. And one of the ways to solve quadratic equations is to use the square root. So let's kind of review what that is. Oh, there's a nice triangle for us. So don't save that. There we go. So let's talk about square roots. Does anybody know what a square root is? Or you're like, yeah, I kind of remember that. Or is anybody a square root expert? Nobody's talking. So I'm guessing nobody's a square root expert. I bet you guys will know when you see it. When a number is multiplies it by itself. Exactly. So it's related to that, Otto. That's the square, and the square root is related to that. Sorry, Olivia just texted me. She's having problems getting on. So let me... So let's see if she can get connected here. So what Otto said is exactly right? We learned a while ago what perfect squares were, and I know we've talked about it a couple times in class, but oops, that's a circle, not a number. So for example, if you have the number 4 and you square it, 4 squared is 16, okay, which is basically 4 times 4, right? And we call these numbers like 4 squared, 5 squared is 5 times 5, which is 25. These are perfect squares, right? Because I don't know, over time, the more you do math, the more they kind of get stuck in your head. So, if you don't have them memorized, knowing what all of the perfect squares are from like 1 to 10 or 1 to 12 will be really helpful, or at least printing out a list of them will be helpful. Oh, Otto, thank you. I don't think I shared my screen. That would be helpful. You guys all see now? All right, cool. This is kind of the opposite of, it's the undoing of that. So the square root is actually when function and you take the square root of 16, then you're looking at which numbers multiplied together make 16. So the square root of 16 is 4. Okay, and the square root of 25 is 5. Okay, here's the 2-minute explanation off to the side of why. Actually take the square root of something. There's an applied little 2 right in here. And when you take the square root of something, another way of writing square root is something to the 1/2 power. Square root into the 1/2 power are actually the same exact thing. So if you have any number, like if you have x squared and root, it's just going to equal the base number. Okay, so if you have, the square root of 64, well, we know that the square root of 64 is 8 squared, and basically the square root undoes the square, and you're left over with 8. So it's actually kind of cool if you have your scientific calculator. If you put, for example, in your calculator, if I can make my screen a little bigger, if you put in your calculator of 81, or you put 81 to the 1/2 power, or 81 to the 0.5 power, all of those will give you the same answer, which is 9, because 9 squared is 81. So just kind of a side note about square roots, and probably knew, but you might not know that it means to the 1/2 power. And a slight add-on to that, this chapter, we're only going to be talking about square roots, but there are other roots. So you might have seen it on your calculator, you might not have, maybe didn't pay attention, but you can also take the cube root of a function, you can take the fourth root of a function, and so on. Okay? And so if you're taking the cube root of a function, that's the same as saying x to the 1/3 power, or x to the 1/4 power. These are all kind of equivalent expressions. Okay, so that is what the square root is, and kind of, how we can use it mathematically. All right, so now we're going to talk about, what if you don't have a nice perfect square? What if you don't have 16 or 25 or 64 or 81, all of those perfect squares, right? What do we do, and how do we simplify square roots? Okay, so for example, if I wanted to take the square root of 27, okay, is 27 a perfect square? Excuse me. It's not, right? Not a perfect square. So I can't say that this just equals 3 or 4 or whatever it might be. So one of the things that I want to talk to you about that may or may not be new is that there are some properties of square roots that we can use to simplify them. I think most of you have seen this before, but we just want to make sure. Okay, so the property that I want to tell you about is that if you have the square root of a times b, you can rewrite that as the square root of a times the square root of b. Okay, so this is one of the properties that we have. What does that mean for square root of 27? Why am I interested in that when that comes to square root of 27? Well, I know that I can't just take the square root of 27. Like if you type that in your calculator, you're just going to get a decimal, which I know you guys can all do. All right, but sometimes in math, we want to leave it in the square root form, but we want to put it in its simplest form. So what we can do is we can break down our number into basically its factors. So I know that 27 is 3 times 9. All right, 3 times 9 is 27. And the reason I like 3 times 9 is 27 is that 9 is a perfect square. All right, the square root of 9 is 3. 3 squared is 9. So I like it because I'm getting a perfect square when I break it up into components. So I can rewrite the square root of 27 as the square root of 3 times 9. And then my property tells me I can break it up. I can rewrite this as the square root of 3 times the square root of 9. And this I can do. The square root of 9 is 3. So the square root of 3 times 3. And then we usually don't write it like this. The square root always goes last. Square root of 3. So square root of 27 and 3 square root of 3 are equivalent expressions. They are, if you put them in your calculator, they're the same number. But if you are doing pretty much from now on, oh, hi, Olivia, I'm glad you joined. Pretty much from now on, if you are working with a value that's square root, like especially if you're checking a solution or you want an exact amount, like if for example, the book, had x equals square root of 27. If you're going to check your work, they're going to have x equals the square root of, or the x equals 3 times the square root of 3. They're going to have this solution, not this solution. That's it, not an x, but not this solution. All right, so this is considered the simplified proper version of square root of 27. Okay, they mean the same thing. So if I just pop Desmos up here, maybe. Let's see. Desmos, right? Maybe. All right, so if I do the it's all hidden in here. There we go. Oh no, it's right here on my front screen. There we go. The square root of 27, right? Or I do 3 times the square root of 3. They're the same decimal. They're the same number, right? This, though, is the in. Okay. Has anybody done that before? Is this review? Is this, or have you ever tried to look for an answer and you're like, oh, I got this, but it says this? Everybody's like, it's too early for square roots. Why are we talking about square roots? So again, having a list, and it's really easy to find, having a list of these perfect squares list. There we go. Either if you're really good at your multiplication facts and you feel really comfortable with your perfect squares, that's great. If not, print out something like this. If it loads for me, that has all of your perfect squares. So that way, if you see, oh, I can pull out a 9, or I can pull a 4 out, or, oh, this is a multiple of 49, or whatever it might be. I would say basically 1 through 12 are the ones, maybe 13, maybe 15, 1 through 15, something like that. Those that you want to be familiar with, because that'll really help your homework to have that. Okay, you can see there's lots of different charts out there. So, or you can make your own chart if you wanted, right? Just go and square each number. Okay, so let me do one more of these like this. Okay, so another example would be, what if I have the square root of 10 times the square root of 15? And I wanted to simplify that. Okay, well, or the square root of 15 are either of those perfect squares? Nope, right? So that can't do anything like that. But what I can do is I can multiply these together inside. So instead of square root of 10 times the square root of 15, I can do the square root of 10 times 15. We're allowed to do that. Okay, which equals the square root of 150. Now I have to figure out, can I simplify the square root of 150? So what I'm trying to do, are there any of my perfect squares that are factors of 150? So if I go back to my perfect squares chart, do any of these numbers go into 150? Well, 100 can't 150, right? But 25 might be a good possibility. 25 does go into 150. So instead of writing 150, I'm going to write 25, because 25 times 6 is 150. And then I can rewrite this as the square root of 25 times the square root of 6, right? and the square root of 25 is 5, and the square root of 6 cannot be simplified. So square root of 10 times the square root of 15, an equivalent expression to that would be 5 times the square root of 6. These two are equivalent expressions, right? They're equivalent to each other. But this would be written in the proper format. Okay. One more piece of that is that there's the idea of multiplying, but there's also the idea of dividing. So the general rule is if you have the square root of A divided by B, you can rewrite that as the square root of A divided by the square root of B. Just like when we were multiplying, you can break them apart, right? When you're dividing, you can break them apart. So what that means is if I have, for example, the square root of 15 divided by 4, okay, does 4 divide into 15 evenly? No, right? It doesn't divide into it. If it was 16, we'd be good to go, but it doesn't divide into it equally. So I could rewrite this as the square root of 15 over the square root of 4. And the square root of 4 is a perfect square, right? It's 15 over 2. Sorry, square root of 15 over 2 will be the equivalent way to write this. Okay. So one last note about square roots. Well, we're going to actually do problems with square roots now, but one last note about just kind of general square root etiquette in math, I guess, is if you want to call it, is that the one thing that is not okay in how we write square roots is when we have a square root in the denominator like this. So this is a no-no. So you can't write it like this. So if you ever simplify something and you end up with a square root in the denominator and no square root in the numerator, we need to get that square root out. Okay? So how you do that is you're gonna multiply by whatever that square root in the denominator is. Okay, so I'm going to multiply this by the square root of 3 over the square root of 3, which is just like multiplying by 1, right? And I will get the square root of 3 divided by the square root of 3 times the square root of 3, right? So what does the bottom become? The square root of 3 times the square root of 3 is 3, and the top is the square root of 3. So again, you might come up with a solution, and that's not just in this section. This is kind of going forward in math. You might come up with a solution that looks like this. This is not the acceptable way to write it. You need to rewrite it with the square root up at the top. Okay. You guys are quiet today. Does this make sense? Oh, good. Yay, we like it when it makes sense. Awesome. Yay, good, good, good. Okay, so I know I said one last thing, but really one last thing. By the way, this little thing right here, we are taking the square root, but this little symbol is called the radical symbol. So sometimes you hear someone say radical in math. I mean, they say it for other things, right? It has a lot of meanings, but this actual symbol is radical. That's a radical symbol. So I just wanted to make sure I mention that. Okay, so now in your head you're thinking, or maybe not, maybe you're just like, okay, I got it. You're thinking, all right, Miss Ross, you started off and you told us this whole chapter was about quadratics. And then all of a sudden you go off on this side tangent all about square roots. How does that have to do with quadratic equations? That's what you all were thinking, right? Maybe not. All right, so now we're actually going to get to some quadratic equations where you can use square roots to help you solve the equation. Okay, so what I mean by that is, if you have your notes, number 4 is a quadratic, right? We have 5x squared equals 80. Okay, and so far we've learned one way to solve quadratic equations, and that is to factor, right? So this is review here. This is our equation, right? Our review from section 4.3 and 4.4, okay, is that we learned to solve this equation by factoring, right? And the one thing that we know is that it has to equal 0 in order to factor and work, right? So we can rewrite this as 5x squared minus 80, right? Let's take 5 out of both sides, so we get 5 times x squared minus 16 equals 0, right? This is a review of what we've done the last 2 classes. So we have 5, and then if we want to factor x squared minus 16, that would be x plus 4 and x minus 4 equals 0. And then one of these two has to equal 0. So either x equals positive 4 or x equals negative 4. Okay, I know I did this kind of fast, but this is what we already have done, right? That's how we learn to solve quadratics, is by factoring them. Okay, so today in section 4.5, we're going to talk about using square roots to solve. So square roots to solve only works, square roots to solve only works when there is no middle term. So basically when there's no x term in your quadratic. So this particular method is like a special case. Factoring always works if you can, as long as you can factor, right? 4.5 is using square roots, so it's kind of a shortcut method, but it only works in certain situations. So basically, remember we have ax squared plus bx plus c equals, some number 0, right? This method of doing the square root to solve only works when this basically equals 0, when b equals 0. There's no middle. That's what I mean by middle term. There's no middle or no x term. All right. So if I go back to this equation that I just did, right? 5x squared equals 80. Okay. There's no middle term, right? There's no just plain x term. We have an x squared, which is good because we need it for quadratics, right? And we have a constant term, but we don't have a middle term. So we can use this idea of solving by square roots. Okay, so this is how the method works. We're going to solve basically down to get x squared by itself. So this one's pretty easy. We're going to divide both sides by 5. And we get that x squared equals 16. Okay, and then what you're going to do is you're going to take the square root of both sides. So the square root of x squared is just x, and the square root of 16 is 4. Okay, but you might have noticed that our original solution had a plus or minus. the x actually could be plus or minus 4. So this is kind of another new thing with Algebra 2, or maybe you did, I think we did a little in Algebra 1, some people. Okay, so why is that? If x squared equals 16, right? You guys are probably okay that, okay, if I put in 4 squared, that equals 16. So that's good, right? But also if I put in negative 4 squared, right? Negative 4 times negative 4 is positive 16. So that works too. So that's why there's 2 solutions. Okay, so can you see how this 4.5 is kind of like a shortcut, right? It's a shortcut. You don't have to factor and set equal to 0 and solve. You can just take the square root of both sides, right? So 4.5 is a shortcut, only works when there is no just plain x term. You have to have an x squared and a constant, but you can't have that plain x term. Okay, so let's try another one. Okay, so what if I have z squared minus 7, all the numbers that don't look like the right numbers, equals 29. Okay, and I asked you to solve for z, right? So is this a quadratic? Yep, it's a quadratic, right? Is it, I want to solve for z, so what are my options, I guess? So my options are that I could factor it, right? That would be one option. Another option would be that because I don't have just a plain old z term, right? I have a z squared and I have a constant, but I don't have a plain z term. So because of that, I could also solve this using square roots, right? So in this case, I still need to get my squared term by itself. So I'm going to add 7 to both sides. Okay, and I end up with z squared equals 36. Okay, so then once I do that, I'm going to take the square root of both sides. Okay, and I end up with z equals plus or minus 6. Because the square root of 36 is 6, right? But when I take that square root, I have to take into account both the positive and the negative 6. So again, I could have factored this and solved it, right? But this is kind of like a shortcut method that I don't have to do the factoring because I don't have a middle term. I don't have a middle, middle term. Okay, kind of making sense? Cool. Otto and Anton, you guys hanging in there? All right, making sense? I'm flipping through my book here to pull one out. Okay. So then let's kind of do the okay. So the fancy example is in your notes. It is this one. This is the fancy example here. Might as well start with a new slate. Okay, so I have 3 times x minus 2 squared equals 40. Okay, so the question is, do I have, or can I use my square root properties? So you actually can use your square root properties to solve this equation. This is kind of like the hard case example. This is actually number 33 from your homework. So can I use squares to solve this? So your first tendency might be to want to, oh no, it's not. It's not number 33. It's close to number 33, but it's not 33. So your first tendency with this problem might be to want to FOIL x minus 2 squared. But what we're going to do is we're actually going to try to use our square root properties to solve this. Okay, so what I mean by that is what we're going to do is we're going to take 3 and we're going to divide both sides by 3. So we end up with x minus 2 squared equals 40 divided by 3. Okay, and then what we're going to do is we're actually going to take the square root of both sides. And then when you take the square root of x minus 2 squared, these cancel out and you're left with x minus 2 equals the square root of 40 over 3. So then you're almost there because all you need to do is add 2 to both sides and you end up with x equals 2 plus square root of 40 over 3. Okay, this seems like a crazy answer. Oh, I totally forgot something. When I took my square root of 40 over 3, it should be plus or minus because there's always 2 answers. So this should actually be x plus or minus the square root of 40 over 3. Okay, so sometimes your answers can look kind of crazy like that, and that's okay. Pre-calc, actually, there's a whole bunch of coef equations that look like that. So that was kind of a crazy case. Let's look at actual number 33 in your book that's close to this and see if you can figure out how to do it. So we have 2 times x plus 2 squared minus 5 equals 8. All right, so how would I go about solving this? Well, anybody have a guess of the first thing you got to do? I like it, Olivia. Yep. Either divide by 2 or add 5. So the first thing that you probably want to do is you probably want to add 5 to both sides. And the only reason I said that is because you can divide by 2, but if you divide by 2, you would have to divide this by 2, and this by 2, and this by 2, right? And then you could add to both sides. So it would work, but then you're dealing with a fraction. So I'm kind of like easy math, right? If we don't have to deal with a fraction, let's not deal with it. So let's go ahead and add 5 to both sides first. Okay, so 8 plus 5 is 13. Oh man, I was hoping you would get a nice pretty number. Okay, and then we're left with 2 times x plus 2 squared. Now we're going to divide by 2, all right? And we get x plus 2 squared equals 13 over 2. Now we want to take the square root of both sides. And when we do that, we want the plus or the minus, right? So we're left with x plus 2 equals plus or minus square root of 13 over 2. Can we simplify 13 over 2? No, right? So all we can do is subtract 2 from both sides, and we end up with x equals negative 2 plus or minus the square root of 13 over 2. And sometimes your answers are just that crazy. So it's -2 plus or minus square root of 13 over 2. Okay. Any questions? Okay, so since this is our last, since we won't have class online next week, I want to segue into something that you may or may not have realized. Okay, so I should have saved my old papers, but let's just leave this up on here, okay? So back in section 4.1, right? Way back in 4.1, we did graphing quadratic functions in standard form, right? That's what we did. So any of these expressions that we're dealing with, right, can be graphed. Now, this is not how I would solve it, but I just want to kind of make it full circle for everybody. So, for example, this problem that we just did, number 33, right? One side of my equation is 2 times x plus 2 squared, okay, minus 5. That's one side of my equation. And the other side is I want to know when that equals 8. Right? Can you see I've typed in the left side of my equation on one side of my graphing calculator and the right side of my equation on the other side? Okay. And so what happens then, and then on top of that, I found that the solution is -2 plus or minus the square root of 13 over 2. So let's just type that in. -2 plus or minus, I don't know if no, it doesn't do that, plus the square root of 13 divided by 2. Okay, so that's one possible solution. Now let me make this a little bit bigger. Make this go down. Okay. So again, because this is our last chance to really do this online till after Thanksgiving, which is crazy, the red graph is the left-hand side of my equation, right? It's a parabola, and we know it's a parabola because even though the squared is out here, that's an x squared. So we know it's a parabola, so it's a quadratic equation, and that's what it graphs like, right? We want to know when this quadratic equals 8. Well, the two places that it equals 8 is where it intersects at, right? Which happen to be when x equals 0.55, then it equals 8, and when x equals -4.55, it equals 8. So when we just solve that last quadratic equation, right, we said that x equals -2 plus the square root of 13 over 2, which is 0.55, basically, right, which is one of my solutions. It also equals negative of that, which is -4.55, which is this point here, -4.55. All right, so I just want to show you how those relate. Back to our original example. Yeah, back to our original example that was kind of our easier example. We had, if you remember, we had 5x squared equals 80, right? And we said the answer is plus or minus 4. So we had 5x squared. Where does that equal 80? So this was example number 1. And we said that that equals 80 at plus or minus 4. Okay, so again, 5x squared is this very simple parabola, right? It's at the origin. And we want to find out where it equals 80. So we're going to have to do some zooming out, right? And that point of intersection is when x equals 4, my expression equals 80. And when x equals negative 4, my expression equals 80. So I just want to kind of put that full circle for everybody, that what you're doing, you can visualize what you're doing as well. Right? So these are, when you find out that x could be negative plus or minus 4, that's what that visually means on a graph, is that these are the two solutions where both are true, where one side equals 80 and the other side is 5x squared. It's plus or minus 4. Okay, does that make sense? I think it's kind of cool that you can see it graphically, right? It's like, oh, I can visualize it. Cool. It's awesome. All right. I am going to introduce the next concept, so that way on Monday you guys aren't like, huh, what? So here is the question for you. What if I told you that if I asked you to solve this, x squared plus 9 equals 0? And I wanted you to just tell me what x's are. So in your head, you might be thinking, ooh, this is the perfect candidate to use my square root. I don't have to factor this. I'm going to try to use square root, right? So I would rewrite this as x squared equals negative 9. And I would take the square root of both sides of my equation, right? And I get x equals plus or minus square root of negative 9. Okay, you're like, ooh, cool, negative 9, that seems like it would work. I go to, you might know this already, but if you don't, you're like, oh, I'll just check in here, see what the square root of, what's the square root of negative 9? Oh no, my calculator says undefined. All right, guess what? You cannot take the square root of negative numbers. All right, I don't know if you've tried it before, but you can't do it. And why is that? Well, it's because the idea of square root is that, 3 times 3 equals 9, right? And the square root of 9 equals 3, right? So you're thinking of what two numbers make inside the square root. Well, what two numbers multiply together? What two versions of 3 multiply to negative 9? Well, negative 3 and positive 3, but you can't. Whenever you square a number, if it's positive or negative, you're always going to end up with a positive because you're multiplying two numbers, two negatives or two positives together. So we can't, in the real number world, we can't ever take a number, okay? So what mathematicians have done to combat that is that we have something called an imaginary, okay? Imaginary number is I square root of negative 1. Okay, so if in this particular case, circle equal 3 times I, because you can take this and we know that the square root of negative 1 is I. So this idea of I is a pretty powerful mathematical concept. I is not a real number, right? It's first of all, it's called, right? So it's not a real number, but yeah, it's not in the real realm. Okay. And kind of to bring that full circle, again, we were just talking about graphing. If I graph x squared plus 9 equals 0 on my graph, okay, if I graphed x squared plus 9 on my graph, and I want to know where does that equal 0, right? My graph is up here, equals 0, and I have a big gap. So graphically, there's something not right here with my solution to my equation, right? So sometimes remember how we talked about sometimes you have two solutions? A lot of times you have two solutions to a quadratic. Sometimes you only have one, and sometimes you might not have any. Well, in reality, you might have some, but they just might be in the imaginary number scale. Okay? So we kind of a quadratic that we're trying to solve like that, we're going to move on to the imaginary. We're going to use the imaginary numbers to help us solve. Okay? So we'll talk about how to solve with imaginary numbers, but I want to even talk basic idea with that, which this is really easy when people say it. So there's something called a complex number. Complex number. Okay, a complex number has two parts. It has a real part and it has an imaginary part. Imaginary. Not either. Imaginary part. Okay, so a complex number could look like this. 3 plus 5i. This is a complex number. It has a real part and an imaginary part. You could also have a complex number that would be, I don't know, 10 minus 4i. Also a complex number. We could have, negative 5 plus I. Also a complex number. Those are complex numbers. They have a real part. So the 3, the 10, the negative 5, that's the real part. And then they have an imaginary part because you have your fancy I in there. Okay. So let's just stop there. I think that's a good spot to stop. On Monday, what we'll talk about is that we can add and subtract complex numbers, we can multiply complex numbers, and we can solve for complex numbers. So we'll talk about how to do all that on Monday, okay? So today, yeah, I think we should be good. So I hope you guys have a good rest of your week, and I will see you guys on Monday. And let me know if you have any questions when you're going over all the homework, all right? Thanks for coming. Bye.